So again, I'm not going to cover all the slides in here, but I do want to go through, because this is some really helpful information, because being at the college level, you're going to probably find that you might have to study a little bit different than the way you have previously studied. And it's always good, because I didn't really have a really good study method until, believe it or not, until I got into graduate school. So I did okay in college, but it wasn't the best study methods that I used, that I employed. They weren't the best. And so it's like trial and error. Find out what works for you and what doesn't work for you. So I want to talk about active learning and passive learning. And it's similar to like hearing somebody and actually listening to somebody. I mean, hearing somebody could be, some of you might be sitting there and hearing my voice, all right, but you're not really consciously understanding what I'm saying, all right? But when you're actually listening to somebody, all right, now you are actively going to be taking in that information. And so a good way to determine if somebody's actually hearing you or listening to me or listening to you is to ask them, what did I just say? You know, and that's kind of where we're going to go with this. We're going to talk about some of the ways that we can actually get it for you, that you are more in the active learning process. And believe it or not, active learning requires less time. You just won't have to use, because at this point in this course, time is going to be of the essence. You know, you're going to probably want to spend at least 10 hours a week studying for this course, outside of actually going through these lessons, all right, reviewing the material, you know, consolidating notes, or doing whatever kind of note-taking method that you like to employ. I know that Dr. Seiler was going over some of that with you, okay? So keep that in mind. I really encourage folks to get into the whole active form of learning here. So basically, when you're actively learning, you're actually taking control of your learning, all right? And it's going to help to improve, I mean, ultimately, your grade. And that's what we want. We want to improve the grade, all right? Don't want you wasting your time, all right? Nobody wants to waste their time. So let's look at a couple of examples of active learning. When we talk about active learning, you're going to be doing something, all right? So for example, attending class. Well, this is an online class, so you'll be going through the lessons on the online material, but coming to the chat sessions, it's going to be largely important and helpful, right? Taking notes. Now, a lot of the times, you are more than welcome to take notes, all right, as we do these chat sessions, because it's part of your assignment. But I would encourage you to do it, and I will be sending out. Again, I post this on my YouTube page. All right, so after I'm done posting, it'll be after the assignments due, obviously. Then you can go back and use these videos, and while you're watching the videos, you can use that opportunity to take notes, and that will definitely help the actual physical act of writing things out starts to imprint information into your cerebral cortex, which we get to learn about all that in chapter 13. All right, obviously read the assignments. I'm going to have the assumption that you have read the chapters. Okay, everything in your textbook, okay, is game to be asked on any tests, okay? Study the materials constantly. Obviously, listen while we're in these chat sessions here, and then also learning from the mistakes. Now, example for learning from mistakes is going to be going over old tests. So when you go over a test and you want to look and see what you missed, then you can say, all right, what was I thinking? Why did I miss this? Did I just not know the information? Or did I get a concept confused? I really want to know that concept better, okay? So definitely try to help utilize that, because that will definitely make you a much more successful student and help you in this class here, okay? So definitely, if you're self-motivated, that will help quite a bit. And even being resourceful. When I talk about that, you know, if you have a question on the material, great, you know, ask me. But if it's on the weekend or whatever and you really want to understand it, you can go and Google it. I mean, Google has a lot of information. I'm not saying believe everything that you can Google, but at the same time, if you want to answer your own question, I love it when students ask me things. But at the same time, you can Google it and see what's out there, do some research, look through the book, and by doing that, believe it or not, that will help you to understand that concept, answer that question, learn that material a little bit better. So go ahead and try that, because it will definitely be helpful. So a couple things that we use when we talk about active study habits is asking questions. I say that all the time. And if you've ever met any other students that have taken my classes, you know, they'll tell you the same thing, that I always encourage students to ask questions. Right? That's going to be very, very helpful. Right? Obviously, take good notes. Right? And good notes are accurate. Okay? I like to use a lot of examples when I'm explaining things because it helps to understand the material a little bit better. And it will help to clear up any confusion on certain things. All right? I want you to stay on task and complete all your assigned homework assignments. All right, we send out weekly announcements. You have the course schedule there. Make sure that you stay on top of that. All right, we don't give you those assignments just for busy work. All right, those assignments will help you learn the material. Believe me, trust me. I've been doing this here. My undergrad degree was in education, and I've been teaching at Greenville Tech for 5 years, and before that, I've taught in other locations. But it will definitely help. Okay. All right, so a couple things that you'll get out of active learning, okay, is you will gain an understanding of the material, all right, much more easily, all right, and you can gain more of the content when you engage in active learning. This is one of my favorites. It will take less effort. Believe it or not, it will. You won't have to, I hate to use the term waste time, but you won't have to invest as much time. So you can learn more in less time, which is going to be very beneficial to you, right? Trust me, it is going to be that much easier to, when you're starting to review, especially when you get towards the end of the semester and you have your finals coming up, because they are cumulative, they cover everything in the course. You will have, at that point, when you go through to review the material, and when time is kind of ticking down, right, you will not be as stressed out. And if your stress levels are low, usually your test performance and your performance in the course is usually better. Okay. All right. So again, I'm not going to be going through all of this for slide to slide, but one of the big things that I really want you to walk away with, right, when you go through this material, is as you gain that knowledge, all right, you'll feel better about yourself, all right? Because there's been many times, and I've felt that almost defeatist type of attitude when I've been going through course material, trying to pull the all-nighter, and I've done it a time or two. I would say right now, from hindsight, it does not work, all right, even though it made myself kind of feel somewhat better. Very stressful. But there was times when I just wanted to quit and be like, I can't believe this, I just might as well just give up. Had I been an active learner, I wouldn't have had that. I wouldn't have felt that bad, okay? So you keep hearing me talk about active learning, but I haven't really gotten into what the passive learning is. So when we talk about passive learning, it's basically not doing anything or doing very little. All right, here's a term here, osmosis. That's the actual passive movement of water through a semi-permeable membrane. We'll get into the actual definition of that when we get into chapter 4. But osmosis is usually, it's a passive process. And a lot of folks think that they can learn through osmosis. It's not going to be that easy, okay? Because basically you are not going to be exerting any type of conscious effort, and it just doesn't work that way. I had a roommate in college that used to sleep with his textbook under his bed hoping to learn through osmosis. He literally did this, by the way. Okay, so some of the examples of passive learning: daydreaming, not taking any notes, not doing any of your homework assignments, not asking for help, right? You can ask for help from me. You can ask help from your students, your classmates. I saw that you folks were engaging with each other, talking about study groups. Study groups are great. They're very helpful. You can bounce ideas off of each other. You learn so much. Trust me. Not coming to the chat sessions, right? That's going to be a problem. Not participating, okay? Especially on these online assignments, you know, if I'm going over something and you have a question, type your question in. You know, I'll definitely answer that question, right? Very important, very, very important, okay? So keep that in mind. All right, and lastly, I just wanted to cover this last part, then we'll get into the material here, all right? So a couple things that you want to make sure that you're doing, and not just in this class, but throughout any semester, especially for some of you who are full-time students, full-time workers, and even a full-time parents. You know, sometimes I have all of the above. Sometimes I have 1 out of 3, 2 out of 3. Point being is, all right, don't waste your time. Make sure that you're utilizing your time very importantly. And with that time, you want to try to do a couple of these things that I have listed here. All right, obviously. All right, try to reduce your stress, okay? And so in order to reduce the stress and not be tired, get sleep, okay? 6 to 8 hours, I'll say 7, all right? 7 to 8 hours is the required amount, okay? So 8 hours is the required amount for an Olympic athlete. I am nowhere close to that, all right? But I try to shoot for anywhere between 7 to 8 hours. You'll never catch up on sleep, all right? Because once it's gone, it's gone. You missed it, okay? So you just want to make sure that you're trying to get that period of time. Now, some of you are probably thinking, well, it's easier said than done. I know, I get it, I understand, all right? But that should be a goal, okay? Obviously, eat well. Don't eat garbage all the time, okay? Garbage in equals garbage out. So if you're putting trash into your body is going to respond to that, and it's not going to be optimal and effective. Exercise. I'm not asking you to be, you know, an Olympic athlete or whatnot, but taking walks. There's a study out that says you can improve your immune system's effectiveness by walking, all right, 3 to 4 times a week for 30 to 40 minutes at a pace anywhere between 18 to 20-minute mile walks. And by doing that, you increase your immune system by 30%, and that's just walking. All right, obviously, if you're going to drink in moderation. Don't get wasted every night. That's bad news. And then obviously smoking, okay? Try not to engage in smoking. All right, that's the end of my PSA, public service announcement. All right, let's get into our first review here, okay, on chapter 1. Any questions about anything that I kind of put up there? Just a couple things just to kind of help you out, okay? You'll have to forgive me, I'm suffering from a mild cold. All right, number 1, it's a mild cold, starting to feel a little bit better. Number 2, yes, it was negative, okay? In case you're wondering about COVID testing, it was negative, okay? All right, so here we go. I already had COVID back over the break, so I already had to endure that one. That was interesting. Okay, so chapter 1. This chapter is the concepts in this chapter are going to revisit you throughout Bio 210 and Bio 211. Okay, so we really want to hammer home a lot of these concepts here. So the first concept is homeostasis, all right, health. Right? So the definition of homeostasis is the ability of an organism to maintain consistent both internal, all right, oh, why is this not underlined? It's making me mad here. I like to draw a lot, so you have to bear with me. All right, consistent internal environment in response to changing internal or external conditions. That means that your body has to be able to withstand changes that are going on inside and outside, okay? Your body has to always maintain a specific body temperature, even though you could be going from your very warm car, all right, of 82 degrees, and you could step out into, I think the temperature today was 45 degrees, okay? So your body has to be able to handle that, going from a nice comfortable temperature to stepping out into the cold, right? So that's what homeostasis is. We usually view homeostasis as the overall general health condition of somebody, okay? Would you mind going over how attendance for that chat session was? I didn't get a chance to read all that. Is part B of this assignment also for the people who join the session or just for those watching the recording? Well, everybody has to attend the session, okay? And so everybody has to also do a write-up on the session. So that's a great question. So that is one of the required assignments of the course. So it is expected that you will be in attendance for all these sessions, and then after the session, you will do the required write-up Okay, a minimum of 10 sentences, grammatically correct. They have to be somewhat coherent. All right, so we want to be able to see that you were, engaged in the chat session there. Okay, and then you'll submit it on Blackboard by the due date. Okay, which is on every Sunday. So just think, every week you'll have a chat session on Tuesday. Every Sunday you will have to submit, or you have until Sunday to submit the assignment. All right, but everybody has to, it's expected. Okay, you're very welcome. Thank you for the question. All right, so you're taking an anatomy and physiology course. So throughout anatomy and physiology, we are going to be talking about anatomical structures and physiological processes. All right, and understand that all these structures and all these processes are constantly and continuously being monitored by these checks and balance systems in your body. And if something needs to be adjusted, then we adjust it, or your body adjusts it. Okay? So another term for anatomy is going to be, and bear with me on this, it's hard to write with a mouse, structure. Okay? So when you hear the term structure, you should think, oh, that is referring to anatomy. And when you hear the word function, okay, you know what? I'll type it out. When you hear function, right, you will think physiology. Okay, so function is related to physiology, anatomy is related to structure. We have baroreceptors and chemoreceptors, perfect example. Yeah, baroreceptors and chemoreceptors, Eric, are going to be anatomical structures. They're sensory receptors, and baroreceptors have to do with pressure inside of usual vessels, and the chemoreceptors monitor chemical levels. And it depends on what that chemoreceptor is actually programmed to monitor. It could be carbon dioxide levels, oxygen levels, but yeah, yep, great question. Or yeah. All right, so because we're going to learn about homeostasis, we need to understand the homeostatic system. And there's three components. And you're going to see this concept cross over several chapters from here on out. Right? So when I teach, right now I'm in the middle of teaching Bio 211. And so we are learning about the physiology of the circulatory system. We just finished up the heart. So we're seeing how certain receptors, all right, like Eric just mentioned, the baroreceptors and chemoreceptors, they're going to monitor, all right, certain changes. Okay, so for example, the stimulus, let's use blood pressure, for example. You have baroreceptors in your aortic arch, and you have baroreceptors in your carotid sinus. These are blood vessel structures. And so these baroreceptors monitor the amount of pressure on the blood vessel wall. So if the blood pressure increases, that's the stimulus, okay? That's the change, okay? So the stimulus in this example is an increase in the blood pressure. Then that's going to stimulate the baroreceptors to fire signals more frequently, okay? And it's going to send that information to the control center. So the baroreceptor is the receptor. It's going to detect changes. And in this case, it's going to detect any changes in our blood pressure. Then it's going to send that information to our control center, okay? So in this example, our control center is going to be our central nervous system. All right, so there's two parts to the control center. You'll have either the nervous system or the endocrine system. The nervous system is like the electrical part of our communication system in our body, and the endocrine system is going to be like the chemical, all right, communication system in our body. Nervous system can have a quicker response, okay, real fast. Endocrine takes a little bit longer, but its effects are more sustained or longer lasting, like adrenaline. For those of you who've ever been in an accident, all right, a car accident, and you weren't in a lot of pain right away, All right, and you know the paramedics are checking you out like, you okay? You okay? Yeah, I think so. I don't feel too bad. And then the next day you wake up and your body's racked in pain. That's because the adrenaline was still coursing through your bodies minutes and hours after the accident. So that's why it's more sustained. So in our example with our blood pressure going up, okay, the nervous system is going to be the control center. So it's going to get information, all right, from the receptor, okay? And then what it's going to do is it's going to interpret that information and then decide how it wants to respond. Well, if our blood pressure is increased, all right, the control center is like, well, I want to decrease that blood pressure, okay? And to do that, it will then affect the changes through what we call the effector, okay? And the effector is the structure that is going to bring about the changes to change that stimulus, right? Which are going to be, so in this course, our effectors are going to be muscles and glands. You'll hear me refer to them as effector organs, but those are muscles and glands. Okay, so you have different types of muscles. You have skeletal muscles, cardiac muscles, and smooth muscles. And then you have a whole variety of different glands. All right, but for right now, our effectors are going to be muscles and or glands. And that's what the effector does. It's going to bring about the change. So in our scenario, our blood pressure is elevated. We want to reduce the blood pressure. Well, no problem. All right, the nervous system then tells the heart, hey, heart, slow down. Reduce your heart rate. Beat slower, okay? And don't contract so hard. So that will start to pump out less blood. And at the same time, it's going to tell your blood vessels, hey, relax, all right? Just relax. Just open up and relax. And by doing that, all right, it's called vasodilation. It goes from a blood vessel. The lumen of the blood vessel is the, my computer's being a stinker. All right, that's the opening. Here's a blood vessel. All right, we cut it in half. We're looking at the inside. This is where the blood flows. That's also called the lumen. That's the space on the inside. So if we want to decrease blood pressure, we'll just have the blood vessel get bigger. Much bigger. So it goes from that to this. And that will then decrease the blood pressure. So that's going to be our homeostatic systems. There's three parts: the receptor, the control center, and the effector. And it all starts with a stimulus, which is some sort of change. It could be outside the body or inside the body. The one I just gave you was something that happens inside the body. The example listed here is a change in temperature in the skin. That's going on outside the body, like when you step out of your nice warm car into that 45-degree temperature there. So these homeostatic systems are regulated, all right, but by what we call feedback mechanisms, okay? And these are these systems of control. The brainstem would not be the effector, Eric. The brainstem is going to be the control center. In the brainstem, you have your vasomotor. If we're still talking about the baroreceptors, you'll have your vasomotor center there, and then your cardio acceleratory and cardio inhibitory. That's part of the central nervous system. So that will be part of that's the control center. Sorry, I didn't see that. So we have our feedback mechanisms, okay? And so these feedback mechanisms are going to control a lot of the processes that occur in our bodies. So the negative feedback control center is going to affect most of the processes in our body, okay? So I want to talk about what a set point is. Does anybody know what the normal body temperature is? Can you think of the normal body temperature? Yeah, that's right. So 98.6 or 37 degrees Celsius. You're the first student that's ever given me Celsius. Does anybody know what the normal value for blood pressure is? You got to know it. You're right. You got to know it. Yeah. Well, actually, yeah, 120/80. So 120/80. Okay, so those are going to be the set points. But guess what? All right, if I have a blood pressure of 100, all right, over 70, okay, I'm still okay. Yeah, it's a little bit low, but it's a little bit low on the normal range. Okay, the range for blood pressure is going to be, you want to know this, 90/60 to 140/90. That's the normal range. So 90/60 and is going to be the lowest of the normal range, and then 140/90, all right, anything that or above is going to be considered to be hypertensive. Okay, so if you fall within these values here, all right, you're okay. Well, guess what? Temperature, same thing. Okay, so 96.4 degrees Fahrenheit to 99.1 is going to be the normal range for our body temperature. Okay, so as long as you fall within that, you're okay. The set point is going to be those common values that we know. That is going to be, all right, where our range, our normal range is going to revolve around. So your body's always going to want to keep it, like for example, pH. pH value for your body is 7 point, whoops, golly, hold on, let me erase all that. pH value for your blood, I should say, normal value is 7.4, okay? But there's actually, the range for that is 7.35 to 7.45 for your blood pH. Okay. So keep in mind, this is the set point. All right, this is the normal range that set point should fall within. And that's what you're seeing here in our little graph down here at the bottom. All right, this black line that's going along the x-axis, that's all right, that's our set point. But see, your body will fluctuate, all right, depending on what we're talking about. If it's the pH value, if it's your blood pressure, because things will happen. All right, something will start to drive your blood pressure up. You might start exercising, for example. Okay, and that would increase your body temperature. So your body's going to start to try to take certain mechanisms into play that is going to try to reduce that. So when we talk about a negative feedback system, all right, the resulting action is always going to be in the opposite direction of the stimulus. Okay, so if your body temperature increases, right, then the resulting action is going to try to decrease the body temperature. If your breathing rate increases, right, the resulting action is always going to be to try to decrease your respiratory rate. Okay, so that's negative feedback. Right, we're always going to try to go in the opposite direction of the stimulus. All right. Conversely, we have what's known as the positive feedback system. Now, this is less frequent. We won't see this as much, okay? But in this situation, the stimulus, all right, is going to be reinforced, okay? So we're basically going to move in the same direction as that stimulus, all right, until something occurs. So for example, breastfeeding, as long as the baby is there nursing on the nipple, okay, and that stimulation of those receptors in the nipple are going to send information to the control center. In that case, it's going to be up there in the hypothalamus, right? Then mom is going to not only produce milk, but also eject the milk, right, through prolactin and oxytocin. So as long as the baby's there, she'll keep producing. Okay, when baby stops nursing and moves on to solid foods, she starts to feed less frequently, then she stops producing as much. Blood clotting, same situation. Labor, same situation. As long as the baby, and you'll learn about this more. All these examples are going to be found more in Bio 211, right? But labor, same type of scenario will occur. all right, as long as the baby's head is pushing against, the cervix, all right, that is going to stimulate more oxytocin being released with uterine contractions occurring, all right, but once the baby's no longer in the uterus, all right, then we've removed the stimulus, then we return back to homeostasis there. Okay, so keep in mind that when we talk about positive feedback, we're going to always move in the same direction, basically reinforcing the stimulus until that climatic event, which happens. Well, what's the climatic event in labor? Giving birth, having the child, right? Once that occurs, then we're done. And we don't need to worry about that anymore. All right, same thing with blood clotting. What's the climatic event? We stop bleeding, okay? Okay, so quick summary. Everything on this slide is what you need to be very, very well acquainted with. All right, when we talk about, all right, homeostatic systems, all right, one, I didn't really talk about this dynamic. Dynamic is ever changing, okay? So these homeostatic systems are going to be changing all the time, meaning they're going to be in flux, all right? Blood pressure, breathing rates, all right, body temperature, okay? So they're going to be changing quite continually. The control center is either going to be the nervous system or the endocrine system, okay? They both can work together to achieve a similar outcome, all right? But that's what we're dealing with here in this course. All right, when we're talking about the control center, it's either something from the nervous system or the endocrine system, unless we tell you differently. So there's three components to our homeostatic system. The receptor that monitors a stimulus, we need a stimulus, okay? And then that receptor will detect a change from that stimulus, and it will send that information to the control center. That control center will receive the input, it will interpret the input, and then it's going to figure out how it's going to respond. All right, and when it does, it's going to send that information to the effector. And the effector is either going to be, well, the effector is going to carry out the change. Okay, the effector is either going to be a muscle. This is an abbreviation for muscle. It's going to be a muscle and or a gland. Okay, so most of these systems are governed or regulated through the negative feedback. Right, the response will be in the opposite direction of the stimulus. Increasing body temperature, we need to decrease it. Increase the blood pressure, our response is going to be to decrease the blood pressure. Okay, so what happens when this fails? You are no longer in balance. We are in what we call imbalance or in a diseased state. And some people will describe it as a state of dis-ease. Whoops. Sorry, hold on. Hold on one second. There we go. State of dis-ease. You're no longer in that easygoing state. So alteration. Now, when you say, Eric, when you talk about alteration, what are you referring to? Like an altered state because of the failure of the homeostatic system? Because that will happen. So here, like with beta cell, yeah, exactly. And I don't know if I have that slide on here. Oh, good, I do have it. Hold that thought, Eric. We'll talk about that in a moment. Yeah. Beta cells not producing insulin. Yep, we'll talk about that in a second. So here's a couple of our normal ranges here, okay, for certain things. All right, body temperature 98.6. I gave you that range. It was 96.4 to 99.1, okay. Blood glucose, you usually want to see it in this right here, okay. blood pressure and whatnot. All right, but basically, all right, when we get these ranges, what we've done is we've just taken a bunch of people who we consider to be quote unquote healthy, and we've just sampled a bunch of their values, okay? Be it blood glucose levels or levels of sodium or levels of calcium in the blood. So we just took a whole bunch of sampling from individuals, and then we've compiled, all right, these normal, this normal range value, right? And so 95% of people will fall into that value there, okay? Then you'll have a small outlier group, usually about 5%. Like I have a brother-in-law who usually runs, his temperature usually runs a little bit lower. So what would be a low-grade temperature for you or I could actually be a fever for him. Okay. So this brings me to Eric's discussion about diabetes. So perfect example. This is when we fall into that homeostatic imbalance. Okay. And it depends on now. If I'm correct in assuming you're referring to type 1 diabetes when the beta cells are not producing the insulin. So insulin, in case you're wondering, insulin is going to be the hormone that helps to monitor your blood sugar levels. It does a couple other things, okay? Helps to decrease fatty acid blood levels, and it helps to decrease protein blood levels. Essentially, I tell people, think of insulin as this hormone that takes stuff out of the blood and puts it into cells. And so glucose being one of those. So what happens is we don't have the hormone to do that, right? So what we'll find is if insulin is not present or if it's in significantly decreased amounts, you'll find that the blood sugar or levels will be high because we don't have that, all right, hormone to take the glucose out of the blood and stick it into our cells. And so one of the issues that we'll find is, all right, these patients will have a litany of problems. It can be anywhere from increased urination, all right. They can have, if you get really bad, they can start to get peripheral neuropathies, damage to the nerves, damage to the peripheral blood vessels. They can start to get ulcerations, and eventually, if they get infected, it can lead to amputations. And that's one of the most frequent causes of foot amputations in the United States is from diabetic neglect, right? But we find out that there's a problem. What we do is we diagnose that problem. Then we have to figure out, all right, how are we going to fix that? We have to treat this person. Well, how do we treat that? We treat that patient with meds. Insulin injections, for example, insulin pumps that are going to inject insulin. For type 2, we have other drugs that we use like metformin, glucophage, all right, that will help to restore the homeostatic mechanisms, okay? Because now we're giving them, all right, insulin because their body's not producing it. So we're going to give them an outside source of insulin, which will then encourage their cells to actually do what they're supposed to do. And the exciting part is you get to learn all about that in chapter 17, all right, when you get to discuss the effects of insulin. Because insulin is it's an amazing hormone. It does so much. It does so much. Okay, so that's chapter 1. Again, that's not all of chapter 1. But that is the review for chapter 1. It's for Dr. Seiler and I, that's the information that we really want you to take home and kind of chew on, all right, and really kind of go over that. If you understand those concepts in that material, there's a lot more material in chapter 1. I think it's one of the easier chapters in the book. But if you have a good understanding of the chapter 1 material, when you start to learn all this other detailed information, it'll make it that much easier for you, okay? I want to jump into chapter 2 because chapter 2 is it's a tough one, especially if you have not taken chemistry. So I have the fortunate pleasure of kind of teaching you chemistry. All right, trust me, it's going to be on a limited level, and we don't expect you to be chemists by the time you are done with chapter 2. But we're going to give you the information that it's going to help create a good foundation for you. So let's first start off and talk about matter. Okay? And again, I'm not going to get into all of physics and what matter is and whatnot, but you need to understand, all right, something about matter. Okay? It has both mass, and when we say it occupies space, that means it has volume. Okay? Volume. All right, so there's 3 forms of matter. And if you look there, that's pretty self-explanatory. So again, you don't need to read the textbook to know this, but there's 3 forms of matter: solid, liquid, and gas. All right, so let's equate that to what we find in our body. Well, solid would be bone, cartilage. All right, I guess you can kind of say that skeletal muscle is going to be solid. It just won't be as hard as bone. All right, and then we have liquid. That will be like your blood, for example, or your lymphatic fluid, your cerebral spinal fluid, okay? And then gas, respiratory gases, nitrogen, all right? Some of you probably know this, that the most abundant gas in our atmosphere is nitrogen, but it also sits in the synovial fluid of your joints, all right? Oxygen, that's one of our respiratory gases. Carbon dioxide, another respiratory gas. Hydrogen, all right? So those are our 3 forms of matter. So when we're talking about matter, we're going to start with the smallest, all right, existing particle. All right, I'm not going to get into quirks and all that other stuff. We're going to go with just the basic stuff. All right, so we're going to go and talk about the atom. Okay, it is the smallest particle that's going to exhibit the chemical properties of what we call an element. And there's 92 known natural occurring elements. All right. Like gold, silver, carbon, oxygen, hydrogen, helium, all right? All of that stuff. Those are our elements. And so these atoms are going to be the particles, okay, which will have all the chemical properties of that known element. And what we did is we're not going to even go over the periodic table, but what we did is we mapped it out. We made a big table. You've probably seen it in high school, colleges, classrooms there, and they'll show, okay, this table of all these known elements, okay? So when we talk about these atoms, all right, for the most part, we think of them as a neutral particle, okay? So now what we're going to do is we're going to talk about when we charge them. We can either make them a negatively charged atom or a positively charged atom. When we do that, we call them ions. So you need to know, all right, the definition of an ion, because this is going to follow us through the rest of this course in 211. All right, ions are atoms with a positive or a negative charge. That's it, end of story. Or you can say, if you really want to make it simple, an ion is a charged atom. That's real simple, okay? And it can either be positively charged or negatively charged. So how do we charge something? Okay, we're either going to add or subtract an electron to it. Okay, or that atom is either going to lose an electron or electrons, or gain an electron or electrons. Okay, so an electron is a subatomic particle. So I'm drawing a circle here, and I'm going to put an N in the middle of it. That is what we call the nucleus. That is the center of our atom. Much like the sun is the center of our universe. Then you have these little things, all right, that orbit around the nucleus. And those are called electrons. So how you have the planets orbiting the sun, we have electrons orbiting the nucleus. And our electrons, all right, have a negative charge to them. Now on the inside of our nucleus, I'm just going to blow it up a little bit, make it bigger. You have protons and you have neutrons. Protons have a positive charge to them. Neutrons have nothing. They're neutral. Okay? So the protons are positive, the electrons are negative, and the neutrons are neutral, no charge whatsoever. So you know the saying, opposites attract. Right? So the electron is attracted to the positively charged protons inside the nucleus. So they circle around the nucleus because of that attractive force. Okay? So going back to the ions, all right, the fact that we have these positive or negatively charged ions will result in these substances having significant physiological functions. For example, potassium. Potassium is a positively charged ion. It's also known as an electrolyte. Sodium, the same thing. Okay? It's a positively charged, all right, atom. Okay? So when we talk about these ions, they're going to actually serve a role in certain physiological functions. And we're going to talk about them all throughout the semester. Okay, so don't worry, we're not going to go through them right now. Okay? But when we're learning about the action potential, that's the nerve signal that our nerves have, we're going to learn how that occurs. And that has to do with the movement, all right, of these ions. As they move in and out of the cell, they're going to create this current and they're going to create this signal. And that's how we're able to communicate, all right, between our nerves and certain parts of our body. That's how our brain can communicate with our toes, all right, through these nerve signals called action potentials. All right, but that's later on. So we just learned what an ion was. It's a charged atom, okay? And so now we're going to talk about what we call ionic bonds. An ionic bond is when we get a positively charged ion, which is called a cat ion. Think of cats as cozy and cuddly and furry, all right? And you just want to snuggle up to them, all right? So when I think of cats, I think of positive thoughts. So a cat ion is a positively charged ion. Anions are going to be negatively charged. So negatively charged ions or anions, positively charged ions are cat ions. Okay? So like I said before, opposites attract. Okay? So the opposite, the positive charge will attract the negative charge and vice versa. Okay? So when we talk about these molecules that bind to one another, that connect to one another, all right, these ionic bonds occur. And that's what, when we say these electrostatic forces, basically what I'm saying is these opposite charged elements are going to be attracted to one another. Like a North Pole and a South Pole magnet, they get drawn towards each other. That's what we're going to see here with our ionic bonds. Table salt, perfect example. Sodium chloride, okay? Sodium, saying that before, Na is sodium, you need to know that, okay, is positively charged. It's a cat ion, okay? Chlorine is negative, okay? So what will happen is that positively charged sodium and that negatively charged chlorine are going to be attracted to one another, and they're going to form a bond, okay? And so we'll talk about how this works out. I think I have that picture here. Yes, I do. Yay. All right, so I'm going to zoom in here. Okay, so here's your, where are you? Here's your sodium. Here's your chlorine, okay? Just understand that you have the outer, remember, think of these are the electrons. They orbit around the nucleus, like planets orbit around the sun. All right, so on our outermost orbit here, you have one electron. And on the outermost orbit of the chlorine, you have 7 electrons. Okay? So there's 2 things I need to tell you. If you look really close, you see this first ring here? These rings are referred to as orbitals. That's just the path that the electrons like to spin around on. All right? The first ring only holds 2 electrons. You need to make note of that. Write that down somewhere. The innermost shell or orbital, these are also known as shells, the innermost shell or orbital can only hold 2 electrons. True for sodium, true for chlorine. Okay? You need to know that. I've seen that asked on a test before. Okay. The outermost shell is called the valence shell. Oh, I spelled that wrong. Valence shell. Okay, that is the outermost shell. Okay, so you have this rule, and it's called the Octet Rule. The Octet Rule means that any atom wants to fill its valence shell. It wants to get 8 electrons in that shell. So it's going to try different ways to do that, because when its shell is full, then it's stable. And nature loves stability. Okay? So sodium has 1 electron in its valence shell. Chlorine has 7. Now, following the octet rule, we want to fill that outermost shell. So guess what? All right, chlorine only needs 1 more electron to fill its shell. So what happens is sodium is going to donate its 1 electron. Okay? Oh my gosh, you guys can't hear this, but I'm going to murder Siri. She's listening in on my conversation to you folks. Siri, or Alexa, quiet. All right, sorry about that. Okay, so once the sodium donates its outermost electron, did she really? That's funny. She's always listening. So once sodium donated its 1 electron to chlorine, it filled, that's so funny, it filled its valence shell. So now it has 8. And guess what happens now to the sodium, to this outermost shell? It disappears. Okay, so you can see there's 1, 2, 3 shells here. So it gets rid, all right, of its 1 electron. And now if you look at sodium, its outermost shell, its valence shell, has 8 because it had 8 here. All right. And then now if we look at chlorine, well, it's now called chloride. Okay. It has its valence shell full. So they're both stable. And so because of that relationship, a donation that it actually gave up, all right, that one of these atoms gave up an electron, all right, and the other one gained it, it forms, it created, all right, that negatively charged ion and that positively charged ion. So now that they have polarity, they will now be attracted to one another. And that causes what we call the lattice crystal configuration. Oh, okay. Oh, cool. Good, good. Sometimes it helps. I'm telling you, sometimes it helps. And again, I'm not trying, my YouTube channel is not monetized, so don't worry. I only made it for you guys, and plus I just wanted to have a place to store all my lectures. If you want a little bit more detail, you can always pull up one of my YouTube lectures. It's a little bit more detail for chapter 2. Okay, so feel free. It's there for you, right? If you want to go into a little bit more detail. All right, so that's one type of bond, is the ionic bond. All right. Now, in kindergarten, I learned a very important lesson, and that was sharing is caring. Okay, so I am going to talk about the sharing bond. Okay, and the sharing bond, because an ionic bond is when you gain or lose an electron or electrons, right? In this case, neither element wants to give up an electron. or gain an electron. So they end up sharing. Okay, so this is what we talk about. A covalently bonded molecule is when electrons are shared, all right, between, all right, two or more different elements. Okay, for example, carbon dioxide, carbon and oxygen. Those are different elements, all right, but molecular oxygen are going to be the same. Okay, so we're not including that. So when we get this sharing of electrons, then we're referring to what we call a molecular compound. A molecular compound. Good so far? Okay, cool. Okay. I love it. Okay, so again, to reiterate, covalent bonds are shared electrons. Okay, so we're going to see this when both of the elements, or how many there are involved, want or require electrons. You usually see this when you have 4 to 7 electrons in the valence shell, in the outer shell. So guess what? We see this quite a bit in these very popular elements in the human body: hydrogen, oxygen, nitrogen, and carbon. Guess what? The majority, over 50% of your body, is made up of water. H2O. Okay? So a lot of the bonds in your body are going to be covalent bonds. They're shared electrons. Okay? Nitrogen, carbon dioxide, not carbon dioxide, carbon. Okay? So this is what we're going to see this quite frequently. All right, in those very common elements there that I listed for you. All right, so this is showing you an example of covalent bonds right here. All right, so here's one hydrogen atom. Okay, so remember, the first orbital or shell, all right, the most electrons that can fit in it are going to be 2. So hydrogen is going to search around, all right, for another electron from somewhere. Well, if there's another hydrogen by itself, well, those two will come together. All right, and they'll share electrons. Or you'll see carbon. Carbon has 4 electrons in its valence shell. Well, it can form, it needs 4 more electrons. Well, it can get 1 from 4 different hydrogens. That's how we get methane. Oxygen has 6 electrons in its valence shell. So that's why with the formation of water, okay, it'll pick up 2 hydrogen ions, and now it fulfills the octet rule. All right? So again, they're going to be sharing, but keep in mind, some elements are, it's just like, you know, when you're sharing when you're a little kid, right? You're sharing, but if it's still your toy, you know what I mean? And so, yeah, you might share for a little bit, okay, or you're going to want to keep that toy closer to you. Well, some elements, well, when they're sharing electrons, they're going to pull the electrons closer to their nucleus, excuse me. Okay, so they're going to pull them closer to their nucleus, and by doing so, all right, it gives them what we call a higher electronegative value. Okay, so if you're reading through the chapter and you're kind of reading that, keep in mind that certain elements are just going to pull the electrons closer to that individual elements, and when that occurs, that individual elements, all right, even though it's still part of that molecular bond there, all right, will have a higher electronegativity. For example, let me go back to this one here, like water here. You can see, all right, and it's tough to see, and it looks like everything's hunky-dory here. But what we can't really appreciate is that oxygen is going to be pulling all of these shared electrons closer to its nucleus. So that part of oxygen, or that part of the molecule, will be more negative because it'll have more electrons there. And because it's more negative than where the 2 hydrogens are, that will be the more positive end. So it'll have a little bit of a, like what we call polarity, a negative pole, positive pole. Okay, just in case you've been reading that and you're wondering what that was talking about. All right, let's talk about one of my favorite solvents, water. Okay, water, I don't know about you folks at home, I don't cook very much, only because I don't really enjoy cooking. Okay, I'm very fortunate. My wife is an awesome cook, so she cooks. So we have an arrangement. She cooks, I clean. Well, I'm a soaker. I like to soak things because now I'm very fortunate. I don't have to really wash any burnt pots, okay? But sometimes it's just easier to let something soak for a while and then you come back and you scrub it off. Less work, you don't have to worry about it. Well, part of that has to do with water and its ability to act as a neutral solvent. Now we're going to jump into pH, acids and bases here, okay? So let's talk about some of the properties of water. One, it's very important that you understand something, is that water will spontaneously dissociate. What the heck does that mean? It just means it breaks down. Okay, we already know what the molecular formula is for water, H2O. And basically what this statement is saying is, this is what water does. Water breaks down into hydrogen and hydroxide. But if you notice, okay, the hydrogen ion here has a positive charge and the hydroxide ion has a negative charge. That's what it says here. Water spontaneously dissociates to form ions. And so that's what happens. Okay? So we will refer to this molecule here, all right, as a hydroxide, as a hydrogen ion. There's another name for it, and I'll tell you that in a second here. Okay? Not so much. Not so much. I mean, it'll spontaneously do that. It doesn't even have to be stagnant. All right? It'll just start to randomly do this. And again, it has to do, without trying to delve into the whole chemistry part, it just has to do with bond formation and then bond, the degeneration of bonds. So it just happens. So hydrogen ion, hydroxide ion. Okay, I really wouldn't worry about this right here. Okay, but what I'm showing you here is, see how when water breaks down, you have one thing that's positive and then one thing that's negative. So if you have one thing that's positive and the other thing that's negative, they cancel each other out. They cancel each other out, and that's why water is neutral. Okay? Water is neutral because when it spontaneously dissociates, we're going to revisit that that concept there about water being neutral. When it spontaneously dissociates and it forms its ions, it forms one positive or one cation and one anion, and they both cancel each other out, so it keeps it neutral here. Okay? All right, just keep in mind, hydroxide ion, that's what, when you hear me say hydroxide, it's OH negative. Okay? Okay. I'm keeping it real simple here. So that leads me into acids. So an acid is going to be a substance that when it dissociates, you're going to add acid to some water, and when it dissociates, it's going to produce that hydrogen ion, which we just saw, and in this case, an anion. Well, what's that? That's a negatively charged ion. So another name that we give to an acid is called a proton donor. Well, what the heck's a proton? Without trying to be confusing, remember I told you that protons were the subatomic particles that live inside the nucleus? It would be nice if that was the only proton, but of course not. Chemists decided, hey, let's make it really confusing, and we're going to call the hydrogen ion here a proton. Okay? So another name for the proton, or for the hydroxide ion, that's a proton right there, H+. Okay? So when I drop in an acid into water, it's going to dissociate and we're going to get a lot of hydrogen ions floating around. In other words, we're going to increase, whoops, I don't know why that's doing that. Hold on one second. All right. In other words, we're going to increase the concentration of all these free hydrogen ions floating around in that water. So the easier or the more dissociation that occurs, the stronger the acid. Hydrochloric acid is a great example. It's in our stomach. All right, helps to break down foods. Okay, its pH is very low, and that's the scale that we use to describe the acidity of something. Okay, so when we add an acid to water and we don't quite get as much dissociation, all right, that's a weaker acid. Carbonic acid is a great buffer in our blood. It helps to keep that pH value in that set point range, all right, which is going to be at 7.4, but it helps to keep it in that 7.35 to 7.45. All right, so when we drop an acid or place an acid in water, we're going to get this, which is our proton, and we're going to get our anion, which is a negatively charged ion. So that's if we're talking about hydrochloric acid, okay? When we drop that into water, we're going to get H+, and then we're going to get our anion, which is going to be the chloride, Cl negative. That's what we're talking about, okay? That's what we're talking about. So opposite of that is a base. I want you to think of a base as a sponge. SpongeBob SquarePants, I don't care what kind of sponge. All right, it's a sponge. And its job is to go around and suck up hydrogen ion in a solution. Okay? So it accepts the hydrogen ions. Hydrogen ion is called a proton, so therefore we call bases proton acceptors. So when you add a base to a solution that has a lot of free hydrogen ions, it's going to go around and suck it up. So it's going to decrease the concentration of free hydrogen ions in your solution. So the more a base is able to absorb hydrogen ions, makes it stronger. Ammonia and bleach, and that's why they're wonderful cleaners. Okay, not the only reason why. Okay, and it's also one of their properties that make them so effective in sterilizing things. All right, so a base that doesn't really absorb or accept protons or hydrogen ions very well, they're going to be classified as weaker. All right, bicarbonate. This is another. We'll get into this. Well, you won't get into it in 210, but in 211 we talk about the buffering system of the blood. All right, but also when we talk about digestion too. Okay, so when we're talking about a base in water, all right, it is basically going to absorb the protons. All right, did I put it on here? Oh, this slide is hugely important. Hugely important. So when we talk about pH, pH is the scale that we use to measure, all right, hydrogen ion concentration. All right, so how much hydrogen ions we have in a solution. And so the scale we use is 0 to 14. Okay, so right in the middle of that range is neutral, and that's what plain water is. Plain water is the value of 7, because remember, what did I say about plain water? Plain water, right, H2O will break down into, I don't know if it'll show up on here, H plus hydrogen ion. I don't know. Yeah, it won't show up in here. All right, I can't really type it out very well. But like we said, remember, when water spontaneously dissociates, you get a proton or a hydrogen ion, one positively charged, all right, ion, and then you get a negatively charged ion or an anion, the hydroxide, and they cancel each other out. So that's why plain water has the value of 7. It's neutral. So in the middle, 7 is neutral. Okay? So that's what all this other stuff here is explaining. Water dissociates to produce 1/10,000,000th of hydrogen ions and hydroxide ions, all right? And basically, all right, what that does is breaks it down into equal parts that cancel each other out. So this statement here, star it, incorporate it into your brain pans, all right, that pH and hydrogen ion concentration are inversely related, which means as one goes up, the other must come down, and vice versa. What goes down must come up. So what does that mean? Like it says down here, as hydrogen ion concentration increases in our solution, the pH value decreases. So the higher the hydrogen ion concentration, the more acidic something is. Because remember, acids, when you dump them into water, the hydrogen ion pops off. Okay? That will increase the concentration of the hydrogen ion. And so that pH value will decrease. So acids have a low pH value. Conversely, hydrogen ion concentration decreases, all right, the pH value will increase. So let me show you on a picture here. All right, so here is our beaker. You can see there's a lot of hydrogen ions floating around here, okay? So our pH value is going to be very low, right? Because we have a lot of free hydrogen ions here, okay? Our neutral value is right here in the middle, 7, that's pure water, okay? So whenever we add an acid here, all right, more hydrogen ions will fly off, okay, making it acidic. So pH values will be low. Vice versa, all right, when we add something to the solution and it sucks up or absorbs the hydrogen ions like a sponge, remember, that means our hydrogen ion concentration is going to be less than our hydroxide ion concentration. Decreasing hydrogen ion concentration is going to increase our pH. Bases like to do that. They like to absorb things. So when we're looking at our pH scale, okay, the pH scale here, when we have equal concentrations of hydrogen ion and hydroxide ions, because they cancel each other out, we're neutral, like pure water. Now, when we have more hydrogen ions than the hydroxide ions, we become acidic. So we have a low pH. pH value goes down. Okay? Conversely, when we're dealing with solutions that have more hydroxide ions or few or very little hydrogen ions, all right, they're going to be basic. So they'll have an increased pH, 8, 10, 11. Okay? When we go from just to know this too, when we go from a pH value, all right, of 7 to say 6, all right, it is a 10-fold change, which means, all right, we're seeing that solution has 10 times more hydrogen ions in it than pure water. That's all that means. I'm not going to get into the log equations and all that. All that to teach you this right here, neutralization and buffers, okay? Neutralization and buffers. So what is neutralization? Okay, simple. When you need to return the pH of the solution to its neutral value, okay? So how do I do that? No problem. If my solution, all right, has become too acidic, okay, if it has a pH value of 5, all right, and I want to get it up to a pH value of 7, what am I going to do? Add a base to it, okay? That's what antacids do for the stomach, okay? So they're loaded with they're loaded with substances like magnesium is a perfect example, which will help to neutralize and increase, all right, the solution back towards the value of 7 there. Bases, same thing, okay? If something becomes too basic, if it has a pH value of 11 and you want to return it to 7, all right, same thing. You will just add an acid to it. Okay, that's neutralization. You're going to cancel one out with the other. Buffers is a different story because buffers help to prevent that pH from changing in the first place. Okay, so before we let it get to that value of 5, or before we let that value get to 11, all right, in our previous examples, all right, buffers, all right, are going to attempt to prevent that change from occurring. Okay, so they're going to be usually weaker acids or weaker bases, but they help to neutralize, all right, that large change from occurring before it gets out of control. So we're going to see that quite a bit in our blood because we need to maintain that pH value range of 7.35 to 7.45. So we have carbonic acid and bicarbonate, which help to buffer that blood pH, and it prevents it from getting to the point where it becomes either excessively acidic or excessively basic. Okay, so think of buffers as that prevention mechanism. They prevent the pH from getting out of control, right? Keeps it in that safe range there. All right, listen, I did not get as far as I wanted to today, but that's okay. And I'll tell you why. Because what I will do, that's one of my problems, is I talk a lot. But what I'm going to do, because we're almost done, there's not, and this stuff's really, really important. Actually, there's only, yeah, there's not much. So I'm going to tell you what I'm going to do. I'm going to stop here. And what I will do is I will send out a video. All right. It'll only be, I know we're on a roll. I know. And I'm glad that you feel that way. But I have to actually go to the Barton campus here, and I have to teach at 6 o'clock. So good. I'm glad you're enjoying that. Wait till we get to some of the later chapters. It'll be really, really excellent. But what I'll do is I'm going to send out a supplemental video. It won't be very long. There's not just too much to go, but I just kind of ran. Oh, no, no, I won't speed. Oh, good. Good. I love it. I'm glad these are going to be helpful. And this is actually the first time for the online courses which we're actually having weekly chat sessions. So this is something that's relatively new, and I'm actually a huge fan of it because I used to do it with my online classes. Prior to this, we only used to meet 4 times in a semester online, but I used to do weekly interactions with the students, so I'm glad they're making it more official. So what I will do is I will try to get this, the second part. There's not that many more slides, but I don't want to rush through it, and when I rush through it, I usually start to talk fast, and then it just becomes a pain in the rear end. But what I'm going to do is, I'm going to stop recording.